the 15.4 notes for statistics honors. Just note that we do not do 15.3. Okay, in 15.2, you learned about the regression t-test, which is what we use in order to determine the effectiveness of regression lines. Specifically, whether one variable is a good linear predictor of another. Well, there is an analogous test called the correlation test, which is like I said, similar, but basically it's about whether two variables are correlated linearly. But this one's a little bit more flexible in the state that we can determine if it's positively linear correlated, negatively, etc. So there's a couple things to get started with here. So remember that just like prior, we introduced the population slope in the regression t-test, which was beta 1, because we needed, remember, hypothesis tests are all about taking samples to estimate populations. So we have to do the same thing here. So we have our correlation variable R, but this is a sample statistic. We need a population correlation, which we've never seen before. This is introduced as rho, which is the population correlation. Okay, so we will be using that as our estimate for the population, just like we use mu for our population, where we only calculate usually x bar. Okay, so again, the hypothesis tests for rho are all about determining a relationship between the two variables. Remember that, just as a review, if you had a correlation near 0, then you know that the two variables had no relationship. If it was near -1 or 1, that means it had a almost perfect or strong relationship. So I'm just reading here. It says, the key to understanding a correlation hypothesis test is that there is no true linear relationship for the population of all possible bivariate data sets. Then the population correlation will similarly be equal to 0. Okay, makes sense, right? So if basically there's no relationship in the population between the variables, then rho would be 0. Okay, if you look at the correlation t-test, just in terms of the setup, it's the same procedures. It's just the couple things are the same, a couple are not. Assumptions are the same. So for the correlation and the regression test, you're doing residual analysis. Okay, same thing. We get a different color. Don't love orange on gray. For the hypotheses, it's always going to be, the null is always going to be rho is 0, which implies the population correlation is 0 and there's no relationship. The alternative is that there will be basically, it could be not equal to, less than, or greater than. So that's a change. So before, in the regression test, we only dealt with not equal to. So now we're dealing with less than or greater than. So I just want to expand on that. It says, in terms of an alternative hypothesis, if rho is greater than 0, the population correlation, the variables are positively linearly correlated, meaning that y tends to increase linearly as x increases, with the tendency being greater the closer rho is to 1. So essentially, the rho greater than 0 alternative is talking about increasing lines, slopes that are positive, and remember that it only goes to 1. That's not important for the test, but remember that this is basically the rho is 1 test. If it's the rho is less than 0, then we're talking about a negative correlation, and we're hypothesizing a diving line of a slope of negative. And remember that only goes to -1 in the real world, even though that's not really a part. Now, not equal to 0 basically says that the variables are just generally linear correlated. So, okay, sorry about that. I had to pause the video because my dog was whining in the background, so I'm sure you heard that. But anyway, if rho is not equal to 0, basically you're hypothesizing that the variables are linearly correlated, but it doesn't distinguish between positive or negative. It's just like all the other tests that you learned. It's just, if they don't mention anything about whether it's positive or negative, then you choose this one. If they do, then you choose the other ones. Okay, more barking. Okay, so if you move back up to these, so obviously we're always dealing with alpha, but there is a new value for the test statistic. So this is going to be our correlation t-test statistic. So we note that we didn't go back and do any type of sampling distribution stuff, not that that matters, but essentially the denominator is going to be the standard error or just for the sampling distribution. Of course, the numerator would have been r minus rho in the sampling distribution, but because rho is 0, it would have wiped out and just become r, just like we've seen in the past. A lot of these other important observations I mentioned already, so just we're going to move on. So remember, again, we are dealing with we're to critical value or p-value approach. Note that we are dealing with degrees of freedom n minus 2 again, because we have bivariate data, but it's very similar to the procedures we had before for the regression test. Okay, so again, we're going to return to the age and price of a car. Recall that we had the same exact example when we ran a regression t-test on it. So when you actually calculated the lin reg in the calculator, you would have come up with r is equal to negative 0.924 for your correlation. So we might not have written that down before because we didn't actually need it for anything, but if you did it, that's what you would get. In most correlation test problems, they're either going to give you r, or they're just going to give you the data set, and you would do lin reg to find r. So just note that that's usually the setup. So what would the question be? It says at the 5% significance level, do the data provide sufficient evidence to conclude that age and car price are negative linearly correlated? Okay, so if you see this do data provide sufficient evidence, you know it's a test. And if they start asking about negative or positive correlated, you know exactly what type of test you're going to use from now on, which is the correlation t-test. Okay, so let's go to the procedure. So remember rho now. Rho equals 0 is always going to be the null hypothesis. So this implies that the correlation is 0, the population, and that there is no correlation between the variables. The alternative is going to be either that is less than, greater than, or not equal to. So they are saying negatively correlated, so that means that we are dealing with a left-tailed test, that it's going to be, the correlation is going to be less than 0. Okay, we've already done all of the checks for this, the assumptions. We went through the entire residual analysis, so we don't have to do that again. We will do that in the next problem on a very different, a new example that we haven't done before, so that you get that practice. But for now, we don't have to go ahead and do that. We can just go through the basics. Okay, so it says, knowing alpha is 0.05, we move on to computing the test statistic t using the variables r and n. So if you go back to the formula here that we're going to be using, you'll notice that the only variables on the right side are indeed just r and n. This is very useful because r is the correlation. We can be given that, and n is always given because we know how many data points are going to be. So it should be pretty easy to calculate t in a correlation test. So t is equal to r over the square root of 1 minus r squared over n minus 2. Okay, so all we have to do is just sub in some numbers. So it's negative 0.924 for r. We have 1 minus r squared, which is, by the way, the coefficient of determination, but we don't need to calculate that because we have r already. And remember, again, we have 11. We've done this a billion times, but we have 11 cars that we're analyzing, so 11 minus 2. If you find this value, you're going to get negative 7.25. Okay, so what I need to do is I need to show you a very important relationship here. So this is our test statistic, but if we go back to our notes for if you recall, we did the same problem using the lin-reg t-test. And in that lin-reg t-test, we determined that t was negative 7.23. So look what we got here. It turns out that the computations for the test statistic for correlation and regression are actually going to get you the same value or very close to it depending on rounding error. This is a very profound result just because it makes regression and correlation tests sometimes interchangeable. So in some books, they don't even teach the correlation test. So it's just about looking at the question that they're asking. And if they're asking about linear predictors, then you always go to the regression test. If they're asking about negative, positive, whatever correlation, you go to the correlation test. So this is important just so that everybody sees that this is the case, but that's generally the idea and something you want to make sure you keep in your mind. And finally, moving on with the correlation test. So now that we have our test statistic, we can very quickly find our p-value. Remember, this is now a left-tailed test, which means we do not need to multiply the TCDF p-value by 2. So TCDF, remember, we're dealing with negative 7.25, which is, this is being kind about how far over it's going to be, but let's say it's somewhere over here, so our p-value is going to be in here. So we're going to do negative 1 E99 to negative 7.25 with degrees of freedom of 11 minus 2, which is 9. That's going to give us approximately 0. So what do? We reject H naught because approximately 0 is always small enough to reject no matter what the alpha is. In this case, alpha was 0.05. So what would that mean? So if we reject H naught, well, remember, this means no correlation. This means negative correlation. Little typo here. Alright, so that means that we would reject H naught. So we would reject that there's no relationship, and we would indeed include that there is a negative correlation, linear correlation. So that's important, negative linear correlation between age and car price. Okay, so the best thing to do, I think, is to literally just work on one problem from scratch that we haven't seen before. So at least you have the full process. I am going to shortcut the process a little bit because you should already know how to do some of the procedures, older procedures like the conditions. So I'm going to be sort of short there, but I'm still going to mention what you have to do. So it says, number one, the website collegeresults.org publishes data on U.S. colleges and universities. The following 6-year graduation rates and student-related expenditures per full-time student by the university for 2007 were reported for 7 randomly selected, primarily undergraduate public universities in California. All right, so what do we have basically? So we have graduation rates over a 6-year period, and then we have how much money essentially the college or university is spending on each student, each full-time student. So it makes sense that in terms of like which variable is which, because that's important in the beginning of these problems, x and y, sometimes they give it to you, sometimes they don't. Well, in this case, they don't. So what makes more sense? Well, it makes more sense to me that your graduation rate is going to, your expenditure is going to rely on the graduation rate. So in this case, we're going to deal with x and y, which means, again, that means when we end up doing some work here, L1 and L2 it would be the thing. And just as a side note here, believe it or not, you still do the LinReg t-test for correlation as well. So if you go into the LinReg t-test, when you go down to the type of test that you're going to run, like less than, greater than, whatever it is, believe it or not, they actually show not only beta, but they show rho. So I just want to point that out. So you still use this for a correlation test. Now, here's your data. It says the correlation coefficient for this data is 0.58, so you obviously didn't have to calculate it. You could have put in LinReg and found R, but they did tell you what it was. It says conduct a test on significance to determine if there is a linearly positive relationship between graduation rates, and student expenditure. Okay, so this is pretty straightforward. We can pretty much go through the process here. So hypothesis we'll start with. This is always going to be rho is 0, which implies that there is no linear relationship between or linear correlation relationship, same thing, between the two variables. But what's the alternative? Well, the keyword here is positive. So we're dealing with rho is greater than 0. Okay, now these are the hypotheses, but what are the conditions? So remember, we are dealing with the residual analysis. So this is a really good chance right now, if you have been studying and you know your stuff, it's a really good chance right now for you to pause the video and see if, maybe even go back into the regression stuff if you have to, and see if you can perform the residual analysis on these two values. So what does that imply? That implies first your residual plot, and second your normal probability plot of residuals. So again, if you want to pause the video, go back and see if you can do these on your own using the list, go ahead and do that now. Okay, so if you're back and you tried it, that's great. If you didn't and you just want to follow along, that's okay too. But basically, what are we doing here? Essentially, remember we have to do L3 is equal to Y1 of L1. But we can only do that if we run linreg a plus bx in order to store y1 in the calculator. Okay, so remember linreg, I think it's linreg a plus bx, then you're doing, you're putting L1, L2 as your x and y, and then you're putting y1 in for reg equation. I think it's called reg equation there, whatever it is, but basically you want to put that in there, so make sure that you get y1, because if you try doing this with y1, two things are going to happen. Either it's going to throw an error, or it's going to give you the wrong values. Why is it going to give you the wrong values? Because the y1 you previously calculated for a totally different problem that has nothing to do with this one is probably still in y1, so you're going to get the wrong equation being used. So just to give you a heads up on that, especially on exams, you want to make sure that that is all set up. And lastly, remember that L4 is going to be y minus y hat, which is L2 minus L3. This is your residual column. Okay, so basically you would then go into your stat plot and you would graph L1 versus L4 to get your residual plot, and then do your zoom. If you do that, you're going to get something that looks like this. So I'm going to write this in here. It's the best I could do here. It's something that looks like that. Okay, so that would be, this is scattered as you're going to get it. So since it's scattered, that means we are going to be dealing with a good linear model for this. So we are good here. Then to perform the normal probability plot, normally what I do, instead of changing things up, I turn the first plot off, turn the second plot on, go to the last type, and then just graph L4. And if you graph L4, you're going to get something that looks like this. Okay, so linear enough, I think. So we're looking for a linear relationship, which it is. And that implies that we have normality. So we'll check that off. Okay, so these are a good check. And these are great results when you only have 7 in your sample. That's tremendous results, right? Because the less you have, the more likely you're going to have crazy results that you have there. So, so far, so good in terms of this with the results. Okay, so now that the conditions apply, we can then move to our test statistic. Remember, that is equal to r over this big square root of 1 minus r squared over n minus 1. We were given that r was 0.58, so we can do 0.58 up here. We were given that there were 7 sample size, so square 0.58 here, and then do 7 minus 2. If we do this, we're going to get a test statistic of 1.60. We can then do the p-value very quickly. So remember, we're dealing with a graph. like this. We have a 1.60 over here as our test statistic. This is strictly a right-tailed test. Therefore, we just do one side of the sucker, which means no multiplying by 2. So we're going to go from 1.60 to 1e99. Degrees of freedom 5. So there's your degrees of freedom there. You're going to get approximately 0.0852. Okay, so our if you look at our sort of our example here, you'll notice that they didn't say anything about our significance level from what I see. So therefore, if there's no significance level, we assume it's 0.05. In this standpoint, it looks like, alpha 0.05. It looks like we do not reject H naught here because this is greater than our value of alpha. So do not reject, which means it does not provide evidence. And what do? We just restate the alternative hypothesis, which says that there is a positive linear correlation between graduation rate, and we'll just, instead of writing it out, we'll just abbreviate here, shorter, and university expenditures. Obviously, it's more specific than that, but let's just be brief here. Okay, so there's just one small thing that I want to mention here. I'm going to go in blue because it's a completely different thing going on here. So what I forgot to mention in the residual section, just because I want, maybe not forgot, maybe on purpose a little bit, just because I wanted you to work through this, is that there's actually an abbreviated formula for residual in your calculator. It's called resid. So basically, if you have your L1 data, you have your L2 data, and you didn't want to go through doing two different lists right here for L3 and L4, you could do, and using any formulas at all, you could do the following. In your L3, if you go up and select on it and it blinks, so that it's set and you're over here, what would you do? You would go into, again, if you hit the stat, for the stat button, if you hit second and stat, so second, stat, to go to list, if you look at the names, the one you're on, at the bottom, you will see the term resid. So resid, you would literally hit number 7, which is resid, and you would put it in and press enter, and it would immediately populate the residual. So you wouldn't actually have to do these formulas to get it done. Now, just a note on that though, you have to make sure that your data is in L1 and L2 in order to make that work. So just be very careful when you're doing that, that you don't make and you want to make sure that it's always after the fact, after you do your lin reg. It also requires that you have something in Y1 for the regression equation in Y1 for L1, L2. So just to be clear, why don't I often do this in the beginning? Because I want you to see the formulas and understand them, first of all. And when you see the term resid, you don't see Y1. So you don't get that you have to have a Y1 in there for it to work. So you don't see a lot of the process. So now if you want to practice that, go ahead. You can just use resid, and then when you go and do the plots, obviously instead of graphing L1 versus L4 here, you're going to do L1 versus L3. And instead of graphing L4 here, you're just going to do L3. Okay, so obviously it's changing things up a little bit, but it's quickening the process, which I have no problem with. But it's something else, and from what I've seen from all of you in class, you seem very hungry to be able to do anything humanly possible in the calculator. So I'm just giving you some more stuff to use if you need to be able to do that. But that's it for chapter 15.